Hello, everyone. Welcome to our next lesson about thermochemistry. This one is going to be about spontaneous changes and entropy. Take a minute to look at this cartoon, and hopefully by the end of this lesson, you'll understand why it's funny. Our goals for today are to understand what entropy is and the second law of thermodynamics, which is the law that is about entropy. We're going to learn about how to decide whether a change is increasing entropy. We're going to then talk about what a spontaneous reaction is or spontaneous change and how to tell whether a change is going to be spontaneous. So the second law of thermodynamics, in my words, is this. If you have a system undergoing a change, that system is going to become more disorderly unless you influence it somehow from the outside. Here is a picture of a sequence of food coloring that's been dropped into a flask of water, and you can see what happens as time progresses. Pure water and pure dye is more orderly than a mixture of dye. When the drop of dye is all together before it disperses, it's thought of as having more order than when it's all mixed around. Having these two different pure substances mixed in with each other is more disorderly than having the two things by themselves. Also think about what this means in terms of a liquid. All of these particles are moving around each other. This isn't just a static system. So the second law about disorder, the sciencey word for disorder is entropy. It's a measure of the amount of disorder in a system. The variable symbol for entropy in a system is capital S. Unfortunately, entropy sounds a lot like enthalpy, the measure of heat changes that happens during a change. So it's a little bit of a cruel fact that you have to try and make sure that you keep the two things separate. So how to tell if entropy has increased? This is a classic example of understanding what entropy is in terms of disorder. Situation A is low entropy and situation B is high entropy because there is more disorder happening in situation B. I also wanted to point out real quick this with this chicken. I don't know what's on it, and this whole picture just bugs me because of that. All right. How to tell if something has higher entropy, if it's a solid or gas. Pause the video and think about this and think about which one has more disorder. If you said gas, as a substance changes phase and becomes more fluid, in other words, as it goes from a solid to a liquid to a gas, then it gains more disorder. A solid structure has less movement of its particles. The particles tend to be arranged in a more orderly fashion. And so entropy is low in a solid and high in a gas. And a liquid has lower entropy than a gas, but higher entropy than a solid. What a solution? So which have more entropy, solid salt or water? Well, when you dissolve something like salt into water, you increase the entropy of the two things. So the entropy of both salt and water is lower than the entropy of salt water as a solution. Well, why would this be? Well, a couple of things. First, with the two things separately, salt is a solid which has low entropy, so you're giving it liquid-like properties by breaking it up and putting inside a liquid. Also, with liquid water, when it's pure, it doesn't have as many parts. So that's still more orderly than when you have all kinds of things bouncing around on each other. So solutions have more entropy than either the solute or the solvent that makes them up themselves. All right. This is usually the most challenging situation for most students. I want you to definitely pause this and take a look at these balanced chemical reactions and decide which one of these four shows a reaction that would increase entropy. All right. If you didn't pause it, then I'm going to give you another chance to with a hint. Take a look at these reactions again and think about coefficients and the state notations listed. All right, the answer is D. Potassium chloride becomes 2 potassium metal atoms and 1 chlorine gas molecule. Let's talk about why that was the answer. If you want to tell from a chemical reaction equation if entropy is going up or increasing, you need to look at a few different things. First, are there more product particles than reactant particles? You can determine this by counting up the coefficients on both sides and seeing if there are more particles of products being formed. If you're forming more things, that is less orderly than few things. Think about a pile of bricks versus a brick wall. Second, if there are fewer atoms in the particles, this could mean that you are increasing entropy. So for example, if you had a reaction where water is being broken apart and creating oxygen, then the oxygen molecule would mean that there would be less order than a water molecule because there's fewer things in it. The number of particles from the first point would override this. I'll show you an example of that in just a minute. Are the products in a more disorderly state? So are the products a gas, whereas the reactants were a liquid or solid? This could also mean that you're increasing entropy. So let's go back and look at our choices. So with selection A, we had 8 iron atoms plus 1 sulfur molecule, and we made 8 iron sulfide formulas. So if you look at the number of particles, we have 9 particles on the left, 8 iron atoms plus 1 sulfur molecule, and we made 8 iron sulfide formula units on the right. So this means fewer particles in the products, the reactants. Everything is solid, so we can't look at that, but we can see that we've created fewer things from more things, so entropy has gone down. With B, we're starting with 7 particles, 4 aluminums and 3 oxygens, and we're creating 2 aluminum oxides. So again, we are reducing the number of things and decreasing entropy. Also notice that one of the reactants was a gas, and all of the products are solid. Next, we can look at making water from hydrogen and oxygen. Now, water has more atoms per molecule in either hydrogen or oxygen, but we are making 2 molecules out of 3. So we are decreasing the number of things and therefore decreasing entropy. We're starting with 2 potassium chlorides, and we're making 3 particles and products, 2 potassium atoms and 1 chlorine atom. So this is, again, we are reducing the number of particles and making less complicated things, but we are making more things. So we are increasing entropy here. I should back up. Just to be clear, we're starting with potassium chloride is more complicated than either potassium or chlorine gas. So again, we are making less complicated things, something more complicated, increasing order. All right, next goal, spontaneous changes. Spontaneous changes will keep proceeding without any added or continually added input from the outside. So if you look at the cartoon, someone's skiing downhill, that is spontaneous. They're going to keep going downhill until they run uphill. Some not spontaneously be able to ski uphill because you keep adding energy to the process to make this happen. Let's look at our first example of a spontaneous process.